Hello everyone, my name is Guorui Xiao. I'm currently a master student from UCLA, and today I'm very happy that I can present our work, Highly Efficient String Similarity Search and Join over Compressed Indexes. So this work is done in collaboration with Jing from UCLA, Chunbin from Amazon, and Professor Carlo Zaniolo from UCLA. So this is the agenda for today. I will first go over the motivations for our work, and then I'll present our framework CSS under the setting of string similarity search, and then I'll present the CSS under the setting of string similarity join, and then I will show our extensive experiments of our algorithm over various datasets, and finally we'll have some time for Q&A. To begin with, I want to discuss the motivations for our work. So nowadays, similarity search is widely used in search engines, and search engines is deployed everywhere in realistic world applications. So the goal for similarity search is to find out entities that approximately match the queries. So why do we need this? Let's take the example of movie dataset search. Let's say I want to type in the query Schwarzenegger, and what I really want to find is entities that are similar to it. So this is because users like me may not know the exact spelling, and if we were to use the exact search, for example, then even though the start row 1 is the result that we want, but the exact search cannot return the correct result. But similarity search will solve this problem. Other applications that use similarity search include data cleaning, information retrieval, and many others. So similarity joins aim to find all similar pairs from two collections of entities. So here I will give a more formal definitions for string similarity search. So we're giving a collection of strings capital R, a threshold tall, and a query Q, and a similarity function. So we are trying to find all set of strings R from capital R such that the similarity score of R and the query Q is larger than tall. And currently, most existing work deploy a filter verification two-stage framework as demonstrated below. So the figure below, we have two color boxes. So the blue box denotes that this process is done offline, whereas the red box denotes that it is done online. So here, we first have a dataset R, and we generate the signature index offline. And then, as a user sends a query, the filter will use the signature index constructed offline to generate a set of candidates that may contain false positive. And then this gets passed to the verification stage that eliminate all the false positive and finally return back the search result to the users. So similarly, string similarity join use capital R, but with additional collection of string capital S. So the goal is to find a set of all pairs Rs from capital R, capital S such that the similarity score of the pair is larger than tall. So here, please note there's a key difference. That is, the signature index now must be constructed on the fly. So unlike string similarity search, where the index construction is offline and will not affect user experience, so in string similarity join, this is done online during the join. So we really need a fast and efficient algorithm. Otherwise, the user's experience will get affected. So note that in both scenarios, there's a key component that is the signature index. So what is this signature index? So this is just an inverted list. So inverted list is a series of sorted integers with no duplicates. And we use as an index, we just call it the inverted index. So in the figure below, let's say that, for example, the term concepts, if we use the subterm as the signature, appears in row 0, 1, and 2. So as a result, the table on the right, which is the inverted list, has the term concept mapping to 0, 1, and 2. So this serves as the inverted index, and this is often implemented with a hash map. Now, after inverting the index, the compression of it is also important. So there are many existing works that focus on this. For example, P for delta, conscious WAH and its variations, VB and MILC, and etc. And applications that deployed compressed inverted index include Google, Bing, and Apache SOLR. So what's the goal for this compression then? So let's take this as an example. Let's say I have some algorithm running in the memory, and that I want to fetch some data from the inverted index, which is too large to store in the memory and has to be stored on the disk. So this is the pipeline. So if it's stored on the disk, we have to use expensive disk I/O, and that this entire process will be very slow, and that this often becomes a bottleneck. So on the other hand, if the inverted index is compressed into the memory with the same pipeline, now the requesting and the fetching process will be much faster, so that we not only save the space but also saves time. And now, from previous slide, I talked about all these algorithms. So in the setting of string similarity search and join, they really mean all these filter methods used by the used. So we think it would be nice if there is a unified compression schema that can support a broad spectrum of filter methods. So we summarize the list operations required by some general as state-of-art frameworks in this table. So the count filter just checks how many shared signatures with in a pair. So the prefix filter looks at the prefix information. So positional filter additionally looks at some positional information, and segment filter tries to partition the string into disjoint parts. So the count filter requires list operations such as existence checking and intersections, while other filters require union operations. And this is only for string similarity search. So if we're talking about string similarity join, all of them would require additional insert operations, and currently none of the existing compression methods can efficiently support these operations. So all of these motivations pose some serious challenges that our work aims to solve. So first, there is lack of a unified compression schema for string similarity search and join. And second, we need to perform list operations over the compressed data directly. And third, current compression algorithm cannot be performed on the fly incrementally and efficiently, which is a critical requirement for string similarity join because this affects users' experience. And finally, the compression scheme should be lossless. Otherwise, lossless. So time series compression method cannot be used here. So now after the motivations, I want to present our framework CSS first under the setting of string similarity search. So before everything, I want to give a brief introduction to MLC, which serves as a starting point and a cornerstone of our work. So we developed our work based on MLC. And MLC is a classical offline index compression method. The basic idea here is to deploy a two-layer metadata and data framework with a fixed-length compression. So the metadata just stores 3 elements per block: the head value, the offset, and the bits used per compressed data. And the data is just the area that stores all the compressed data by subtracting each element by the head value. So here is let's take this as an example. So here is a complete sequence because it's offline compression method. And now currently the compressed region is empty, and we are trying to compress the first 8 elements at once. So this is what I mean by fixed length. It always tries to compress a fixed number of elements together. So these 8 elements get compressed into the first block B1. So the 3 here denotes the head value because it's starting from 3, and 0 is because it's the first compressed block. And 10 here denotes that now each element in the compressed block only takes 10 bits instead of 32. So now we roll our window forward and we store another 8 elements together into B2. And we move the window forward again. And note that now we only have 5 elements left instead of 8. So we just store the rest as the final block B3. So as some of you may notice, that is, the split of the MLC is not optimal because it's a fixed length. So we developed our first method based on that to solve the problem. It's a CSS vary for string similarity search. The intuition is to calculate the benefits or the bits saved by generating a new compressed block. And we use the dynamic programming method or DP to calculate the optimal split of the index list. So more specifically, let's look at the same example. Here, let's say we're at the element 16 and we ask a question: shall we include more elements? And the DP method will try different things and tell us that adding more elements will no longer help, and it will incur overhead, and there will be no optimal split. So as a result, the CSS vary SSS will just compress the first 6 elements into the compressed block B1, and that it will compress the next 6 elements into B2, and it will compress the rest elements from 1850 to 8706 into the final compressed block. So a key thing here to notice is that now, as you may notice, we're compressing different lengths of elements. So this is due to the nature of the CSS vary SSS, because we use the DP method to determine the best split. So in comparison, you may notice that comparing to MLC, our compressed CSS vary will save more space. So instead of 10 bits used here, each element now only takes 4 bits to store in B1. And instead of 13 bits here, now each element only takes 6 bits to store in B2. So now, after string similarity search, I want to present our work CSS under the setting for string similarity join, which is a more critical and more difficult challenge to solve. So, as some of you may notice, a naive way to do so is to solve this problem is just to extend the offline method. So the intuition here is that we use a lazy update structure. So the uncompressed region stores all the incoming elements until the buffer is full, and then we just append all the data to the compressed region to perform the compression. So let's take a look at this as an example. So this is a buffer of size 12, and that we already have 11 elements, and another element 4152 comes. Now the buffer is full. So if we just extend MLC into CSS online fixed, so as a result, we just compress the entire buffer into a compressed block that is shown within the red. So if we extend the CSS vary into a CSS online vary, as a result, when the element 4152 comes, we just run the DP method over it. And as a result, CSS online vary will say that we should compress data from 15 to 40 for the optimal split. So we compress the data, and now each compressed data takes only 5 bits. So how about the rest of the 2 elements? So we just put them back into the uncompressed region, and waiting for the buffer to get filled up again, and then we will reperform the DP method. So now, some observations of the 2 methods. You may notice that for the fixed length, it is a lightweight execution, because it makes decision at O of big O of 1, and then it just compress. And the memory consumption is high because the split is not optimal. For the vary length, the execution is heavyweight because every time the buffer is full, it needs to perform a DP method. But the memory consumption is low because every time the DP will try to find the optimal split. In addition, both methods will require additional parameter tuning process to determine the best size for the buffer. If the size is too small, then we will miss the optimal split. If the buffer length is too long, it will incur too much overhead. Now the question is, how can we best make a trade-off between memory consumption and execution time, and additionally without any parameter tuning? Is it doable? And the answer is yes. So we propose a probabilistic benefit model to solve the problem. So the key idea here is just that the decision of whether to compress should be based on the number of bits expected to be saved. And you notice that I use the term expected here because we use a probabilistic model to estimate the expected saving, so that the predictions might not be accurate. But we cannot be accurate because this is an online method. However, even though this probabilistic benefit model itself is theoretically sound, in order to implement it completely, we need to store all the statistics, and that it will incur too much overhead. So instead, we optimize this method into a realistic algorithm that will only look at one new incoming elements. So the intuition is that we just compare the benefits gained from compressing all elements in the uncompressed region with the new element against that without the new elements. This is the CSS online adapt, and that there's no buffer size parameters need to be tuned at all. So let's take a look at this as an example. Suppose that we have elements 14 till 50 already, and now the elements 4058 comes. Now, the CSS adapt looking at this 4058, it will decide that including these elements and any other future ones will unlikely to provide more space saving. So this is because that in our definition, this is assorted integers, and any other future elements will only be strictly larger than 4058. So as a result, CSS adapt will decide to store the elements from 15 to 40. For the 1458, it will put back to the uncompressed regions. And note that this decision is made in big O of 1, so it's very fast, and it has really great performance, close to CSS adapt. So now, after introducing all the our framework CSS on the search and join, I want to demonstrate. I want to show the extensive experiments we have conducted over the algorithms. So here is the experiment setup. So we have a server with Intel CPU processors, 16 gigabytes of RAM, and we're running on Ubuntu 14. So the dataset here includes DBLP, that includes a computer scientist bibliography, tweet that contains tweet post, DNA that contains DNA sequence, and AOL that contains query logs. And we're evaluating over the space overhead, the execution time, the index sizes. The implementation is all done in C++, and we compiled it with GCC 4.8.4. So the detail is on the right table. So the average length here just denote the average numbers of IDs per signature in the inverted index, and the cardinality denotes the number of entities per dataset, and the size it just denotes that the size of the dataset in megabytes. The first experiment we want to demonstrate is the index size. So for string similarity search, you will notice that the CSS achieves the optimal. So this is expected because CSS using DP method will find the optimal split. For string similarity join, you will see that CSS vary also achieves the best result. However, as I mentioned before, so CSS vary it has a very high time complexity, because every time buffer is full, CSS vary online needs to perform another round of DP method to determine the best split, and this execution overhead sometimes is unacceptable for users. However, on the other hand, CSS adapt achieves a very close compression ratio or very compression ratio to CSS vary. But additionally, CSS adapt only takes big O of 1 to make the decision. So this is the advantage of CSS adapt. So let's look at the execution time for string similarity search. Here, the red line denotes the CSS vary, and you can see that execution time here, and the uncompressed is the line with a square. So you can see here that CSS execution time is close, very close to uncompressed, which is a line in square here. So it will not affect execution time in any significant way. As for string similarity join, CSS adapt shown in the orange triangle the execution time is close or sometimes even better than the uncompressed, which is line in square. Why better? This is because we implement our CSS adapt with a very efficient bit operations. So sometimes it could be even better performance than uncompressed. And now I will discuss the scalability for string similarity join. The figure on the left demonstrates the time. You can see that it is actually it scales very well. This exponential shape is because of the nature of string similarity join. So on the right figure, you can see that the filter index size scales also very well. So CSS adapt consistently is saving more space, whereas the uncompressed is growing much faster. So we conclude that the CSS adapts scales well both in execution time and reduction in space. Finally, I want to stress again that we proposed a unified compression framework CSS to support a broad scope of string similarity search and join. And we provided our first framework that can construct the compressed inverted list under online settings, and we devised a benefit model to provide guidelines for the compression. And we have conducted extensive experiments to show that we can achieve superb compression ratio while not affect execution time for string similarity search and join in any significant way. And that's all I have for today for our framework CSS. Thanks for listening, and any questions is welcomed.